incoming beam to that vertical line, almost a flagpole. Okay, then we enter this new material and we find that the angle isn't equal. From geometry class, you know that these would be alternate interior? No, vertical angles. And they ought to be equal. But this line is not straight, so that's less. Does it really happen that way? Well, here we actually have a tray of a container of water. We have a light beam, okay? And if you note, when I bring that down like that, this incoming angle here is a lot bigger than this outgoing angle. And this light path is not a straight line. There's a kink in the path of the light, okay? It is refracting. Now, that refraction effect is the reason that we can bend light paths. But it is absolutely it is the explanation for why lenses work. Now, something else very interesting happens. If the light somehow could originate inside the thicker material, and so I can do that by bringing this thing down here, okay? You notice that the reverse happens. We always have the bigger angle in the air, the smaller angle in the water, okay? And notice what happens if I make this angle down here too big, the light actually doesn't get out. And even though the water is transparent, the light can't pass through the surface. This is total internal reflection. It looks once again like a curiosity in a physics course, but I guess I got to do this from this side so people can see it. This is a lucite tube, and I can take my green laser and run it into the tube, and notice that I end up with this very gaudy, the camera doesn't report it well, but I think you can see it pretty well. I get a spiral. I mean, what's going on with the straight line path of light? And the answer is it's actually a straight line path. If you were up close, you could see that that's not really a smooth curve, but rather a whole series of little turns, where the light takes a straight line path in the plastic until it hits the edge, it bounces and hits the edge, and bounces and hits the edge, and it tracks all the way around. This is the way Fios gets to your house, okay? Verizon is sending signals on very rapidly pulsing laser light. It goes through fiberglass threads, bouncing on the edges, and arrives at your house pulsing at some number of gigahertz, which of course is going to deliver your internet, your cable, your whatever, okay? So this total internal reflection has become the heart of fiber optic communication, and that is a refraction effect. The refraction effect is all because there's a speed change. And we're going to take a look at that after the break, but right now I would like to show you one really neat illustration. So we've got this problem, okay? And here we've got a beaker. Yeah, I guess the room lights are a helper, yes, and that works well. So we've got a glass beaker, a glass container that's got two beakers in it, and you can see those beakers, right? So here's the glass, here's one beaker, and then the other beaker's inside of it, and you're actually seeing through several layers of transparent materials, but you can see them all. I mean, if I were washing dishes, I would have no trouble whatsoever reaching in and grabbing one of those glasses, right? And the reason is that each of them has a different index of refraction, which means every time the light crosses a boundary, it does that, it bends. And so the image that we see through this clear stuff gets distorted at the boundaries. If, however, everybody had the same speed and there was no effect at the borders, what would happen? I'd have no distortions, and who was it said you couldn't see it, right? Okay? There would be no distortions, and I wouldn't see any edges. Well, it turns out that Pyrex glass, the stuff you use in the lab, and what's different about Pyrex, when it's heated, it doesn't expand so much, and so it doesn't crack, right? So you can use it to heat things. Pyrex glass has the same index of refraction as corn oil. And notice, I'm not using the expensive stuff, right? I went to the, you can go cheap on this, okay? And so if we take some Pyrex glass and some corn oil, okay? And so here's our corn oil. And we say, all right, if we put the Pyrex in the corn oil, well, you know what? We already have the Pyrex in the corn oil. Okay? So this is invisible in this. Okay? And if you take a look in we've even fooled the camera. Camera's not reporting anything, okay? And so we can bring this guy out. And of course, if I dump a little of the goo out, when that goes in, now you can see it because the air has a different index of refraction and it's quite clear. But once we get that filled with, okay? And so we can make that disappear. Once again, I think this is the way to talk about index of refraction. You know, like don't just say here's what it is, but talk about what happens if it isn't. Why is it important? What happens if we have no difference of index of refraction? And now, this isn't a number anymore, it's a behavior. Okay? And that's a really important sense to have. So the index of refraction is the reason that light changes path, and if we don't have a reason to change path, bingo, we can't tell that anything's different. Okay? So we're going to take a look at one other feature of this behavior after the break. We're going to take a 10-minute break. Please